ICMP stands for Internet Control Message Protocol. Now generally when we design a protocol nowadays, we design both the control part and the data part together as one protocol. So FTP does not have a control part and a data part separate, it's just part of the FTP protocol. HTTP, same thing, control and data part of the same protocol. But when IP was designed, for some reason, a strange reason, at that time there were no rules and no guidance, so whoever designed it designed two separate protocols, one for forwarding and one for controlling IP. So the IP control part is called ICMP. So this has to be always run with IP, and it provides the feedback from the network. So when IP is not able to do certain things, it sends an ICMP message. So ICMP is used by IP to send error and control messages. So whenever you get an error, it comes through ICMP message, not as an IP message. Okay? And ICMP does not report errors. So sorry, this would be IP. No, sorry, let me see. ICMP uses IP to send its messages, not UDP. All right, so what that means is that ICMP runs on IP. Okay, if you go back to the protocol stack somewhere we had, my God, it's too early. Right here, ICMP runs on IP, not on UDP. Okay? ICP runs on IP. ICMP does not report errors on ICMP message. The question is, if suppose ICMP runs into error, what does it do? Then it forgets it. If IP runs into error, suppose you send an IP packet and it doesn't make it, you will get an ICMP message. But if that ICMP message doesn't get to you, no big deal. That's it, done. And ICMP reports error only on first fragment. So if you have fragmented data, then if you lose 3 fragments out of 5, you will get only one error message. And the ICMP header, so it looks like an ICMP header and the data basically. So some part of your packet will be here, not full packet. Some part of the packet will be here, and then the header will be added to that and will be sent back to you in an IP packet. So you will then take that, put into an IP packet, put an IP header, and then data link header and so on and so forth, and will be sent back to you. And it will be sent back to you from anywhere. So it is not that, so basically it could be multiple hops away where your packet was lost or dropped or whatever, and you will get a message that your packet was dropped. Okay? So that is what ICMP for. Now, let's look at this a little bit more. There is an error code in the ICMP message, and there is a type of message. So the type of message is this type, 1 byte, 8-bit. If it is 0, means it is not an error, it's simply an echo reply. If it is 8, this is an echo request. So you want to send some data to somebody and ask them to echo it back to you, loop back. Then you send an echo request and you get an echo reply. Yeah.
These are all the ICMP headers?
These are all the ICMP types and messages. Actually, the messages basically are understood because only type is there, and that means that. Right? 3 means destination unreachable. So if you sent a packet to some place and it didn't make it, it will come back as destination unreachable. Source quench. This will be sent if you send too many packets. You might get a message saying that, hey, you are sending too many, please slow down. That is source quench. Redirect. If you send to router 1 and there are 2 routers on the network, and you send to router 1 and say, please send it to Germany, and they will say, no, hold on, please send it to that router, it's better for you for Germany. So the better path is through that router. So that is the redirect. Where is redirect? Redirect means from now on, this one is okay, I will send it. But the next packet, please send it through that router, because they have a better path. Time exceeded. This is when your lifetime is exceeded. You have gone through the hops, more hops than you said. So if you send a packet with time to live of 11, and it passes through 11 hops, then it will get time exceeded. You will get an ICMP message which says time exceeded. Parameter unintelligible. So if you put a fragment field or any other field like that, and which has an invalid value for some of the length or type or the offset or something, that you will get that message. Time stamp request and time stamp reply. You can send to somebody and time stamp it, and so that is what the request is. Basically you can send a time stamp request, and then the reply will come back with the time stamp. Information request, information reply, address mask request, address mask reply. So these are all the things that you could ask some other host, and they will reply it back using ICMP. And there are more, by the way. This is not the complete list. All right. So I have explained most of these to you already. Source quench, time exceeded, fragmentation required. So this is what will happen is, if you send a fragment, if you send a datagram which is longer than the MTU of some router on the way, and you had set no fragment, please. If you said no fragment, the packet will be dropped and you will get an ICMP message. All right. If you didn't set that bit, then the packet will not be dropped, it will be fragmented and forwarded. Right? But why would you set that bit? Anybody has an idea why would you want to set that bit? Because you don't want that fragmentation to happen on 2000 packets you are going to send next. Right? So you would rather drop the first packet and get the ICMP and then reduce the packet size, so that your other packets will not have the same fate. So that's what is done actually. To find out what is the right MTU for some path, you send a packet with this thing set, and you will get a reply back saying that this is. Then you send with that one, and then it will go through some routers, and some other router may have even a smaller MTU. Right? You will get another one. So once it makes it through all the way, then you use that for all the packets. Yeah.
In the reply, you get the size, the maximum size of that.
Yeah, it says maximum size exceeded, and that's where in one of these codes, parameters, if any, there might be MTU size. All right, address mask reply. What is the subnet mask on this subnet? And ping. Okay, so ping, you have used ping. All of you have used ping. That uses ICMP echo. If you are going on one path, so what I said was that the first router can drop it and says, I cannot take any more than 1000 bytes. Then you send a 1000 byte message. It goes to the first router, but this third router drops it and says, I cannot take any more than 512 bytes. So then you send a 512 message, and you keep doing this lower and lower and lower until it reaches the destination. So that means every router is happy with the size. All right. So ping uses ICMP echo. Ping is exactly that. In the ping, you use the ICMP protocol. And nowadays, many of the firewalls are programmed to stop the ICMP traffic. All right. So, for example, if from your home, I don't know, it might be different from the dorm. From your home, or from my home, for example, if I say ping boostel.edu, no response comes back. Okay, Boostel doesn't respond to pings. Doesn't waste its bandwidth in responding to pings. But if you do Google, it does. If you go to something else, it may not. So everybody has a choice of whether they want to respond to ping to echoes or not. Trace route. Trace route does not use any of these messages. it uses actually TTL expired, which is basically what it does is TTL expired. Where is TTL expired? Time exceeded. Number 11. What it does is it sends, previous route sends a message with hop to live equal to 1. What will happen is as soon as it reaches the first router will decrease that to 0 and say, oh, this packet is outlived. It will send back to you a number 11 ICMP saying that I dropped your packet because it exceeded the number of hops you specified. Right? Then it will send a message with 2 hops to live. The second router will drop it and send a message back. Then it will send a message with time to live of 3 hops. And that's how it finds out that the Google is 14 hops away. Yeah, no fragment bit part. So one of the flags in IP header is no fragment bit. Let's see, flags. See here it says flags, and then it says for fragmentation and reassembly. Let's see if we have a detail of those flags. Well, we don't have the details in the slides. It might be in the book, but there are many flags there. One of the flags is more fragment flags that we discussed, but there is something called no fragment flag. So what that means is that the routers should not fragment this message. They would rather drop it and send me an ICMP.
Why do they need to send an ICMP?
So that I can find out what is the smallest MTU on the path. You know, MTU is maximum transmission unit, the maximum IP size packet that will go through without fragmentation. And therefore, if I'm sending large amount of data, I don't want it to be fragmented, every single packet to be fragmented. So, you know, I would rather send smaller data right from home. Moving on to trace route, you have already seen, so there is nothing much here. This is part of ICMP. And so these are basically, trace route is not one message. In this case, there were 12 messages that were sent. Right? Everybody agrees with that? Then we go to IPv6. So IPv4 started running out of addresses back in 1990s, about 20 years ago. At that time, we felt that there are no more addresses and we need to change the address size. Several solutions were invited and one solution was selected, and that solution said that we should have 128-byte addresses, 128-bit addresses, 16-byte addresses, and that was a good compromise between some other people who wanted 256, some people wanted 64-bit, and from 32-bit to that size and all that. But anyway, 128-bit address was selected. So IPv6 is this version 6. So what happened to IPv4 and what is IPv6? What happened to IP version 5? Well, there is some IP version 5 somewhere, but nobody is using it, so we don't know anything about it. But there was a version after 4 which didn't get too much currency. So 6 is after 4. And it was argued that 2 raised to 128 is big enough for our lifetime, because 2 raised to 128 is 10 raised to 38 addresses. And if you were to give every single piece of sand an address, you will have 1021 addresses per square meter of the Earth's surface. Okay, so you could have as many devices as you want, right? And obviously they didn't think of something which is not on the Earth. Well, IP can get there, right? So we will run out of that if we go to Mars. But anyway, if assigned at the rate of 10 raised to 6, a million address per microsecond, it will take 20 years for us to assign it. So we can't really get rid of that fast. And since we cannot put it in decimal anymore, so we will use hex. So IPv6 addresses are in hex. And they are 2 bytes at a time. So FEDC colon 00 colon 00, and since they are hex, we use colon. Yeah.
Why can't we still use the notation?
Oh, it will just too many numbers to remember. Can you remember 16 numbers? Can you remember your credit card with only one digit each? 16 digits?
No, but I won't remember.
Exactly. See, good thing is that nobody needs to remember the address. DNS does, but you just remember the name. So this is, they just decided to use hex. And by this time, by the way, we had moved beyond decimal long time ago. This was designed in the old days when they still had decimal computers, let alone binary computers. And this is pretty old. So this is hex, and then they made some shortcuts, and the shortcuts is that if you have leading zeros, you don't have to tell me that I have so many zeros in the beginning. You can just tell me the end. But if you have zeros in the middle, you can skip one sequence. So there are 3 zeros here, 3 whatever it is here, and 2 here. Then you just can say double colon. When you say double colon, means everything else in between is 0, and you can have only one sequence like that. Why one sequence?
It's the only way to look at the story.
Yeah, the only way to find out how many are missing. Because you know 1, 2, 3, 4, 5 are already specified, so 11 are missing. Sorry, not 11, 8. 8 minus 5 is 3 are missing. Yeah, was there a hand from the back for the same thing? Answer, yeah, good, thank you. And when you see a colon in the beginning, that means the zeros are missing at the front. And in this case, 1, 2, 3, 4, how many zeros are missing? 4. All right, where actually when we say 1 0 means 4 zeros like that. Each is the 4 bits, so this is 16-bit. Yeah, 4 bit, 4 bit, 4 bit, 4 bit, 16-bit times 8 is 128-bit. Can leave the last 32-bit in that decimal notation. So you can write down like this too, colon, colon, 127.23.45.88. That these are decimal numbers because there are dots here, therefore they are decimal numbers, and they can be, we will figure it out what that means in 128-bit. And then can you specify a prefix by length? So you can say /50. We'll take 50 bits out of that. Okay?
The left side?
Yeah?
The 50 is the left, the most left.
Yeah. Prefix is always the left from the beginning. All right. So IPv6. IPv6 header style was changed. The header style is very different from IPv4. Of course, the version number is same. Version number field is same 4-bit, but other than that, everything else is different. So the first field is priority. Then there is something called flow label. Then there is a payload length. So in this case, we had total length, which means the header plus the data. Here, this means only data. Next header. Here there was only one header. Here they had many headers. IPv6 does not have to have one header. It will have more headers. So this will be the pointer to the next header, not pointer, the number of the next header. So it will say the next header is number 16. So that is, we know what 16 number header is. All right, and we will look for that after this thing is done. This header is done. And then number 16 might say, well, the next header is 10. We know what number 10 is, and then we will look for that after that header is over. So it could be a whole sequence of headers. Hop limit. This was called time to live here. That is called now hop limit. Then the source address, which is now 128-bit, 4 bytes, 4 32-bit words. Here it is only one word. Destination address, which is 4 32-bit words and one word. And so this is the main header actually. There is more to come. The question was, if you have private addresses, then you don't need that many public addresses. The answer is yes, but this question was raised before we knew about the private addresses. This is, IPv6 was designed in 1990s, before we knew the private addresses. So what happened was that we ran out of addresses and we started thinking about the ways, and the first simplest way that came is that we make a bigger address. Right? So IPv6 came about. As soon as IPv6 came out, people said, no, that is too much. You can just do it with this, with this, with this, with this. So other solutions were proposed. And those solutions, one of those solutions is private addresses. All right? And those solutions succeeded wildly while IPv6 failed wildly. So basically that's why IPv6 did not take off, because those other solutions made the problem go away. So the private addresses really made the problem go away.
So back then, if you wanted an internet connection, you had a direct public.
Everybody had only public address. That was the only thing we knew.
And is this used at all today?
Oh, this is used a lot in China. I mean, you don't have an alternative there. I mean, think about it. I have told you about, right? So in Europe, in China, in any other country you go, you need IPv6. Because they don't have enough IPv4 addresses.
How many does IP4 give you?
Huh? 2 raised to 32. Yeah, which is 4 billion or something, and we have 6 billion people. I mean, it's not enough to cover the people, let alone devices. Each person has dozens of devices. Okay? So everybody understand now IPv6 need for it and why the solution was invented, and the fact that there are multiple headers. I want to talk about multiple headers. So first thing is that IPv6 is different from IPv4 because it is 1995, not 1975. The header size, they said we don't need to put everything in the header, so they had the main header is only twice the size. So this length is 4 plus 4 plus 2, 10 times 32 bits, and this is probably 5 times 32 bits. So only twice. Only version number has the same position and meaning, everything else is different. They removed the header length, they removed the type of service, they removed identification, flags, fragment, blah blah, everything is removed. And that means no fragmentation. So IPv6 does not allow fragmentation. Period. Data length replaced by payload length, protocol type replaced by next header. So in the previous one we had a protocol type where we will say in the next header is TCP, because obviously you don't have IP, you could have IP inside IP, but generally inside IP you will have TCP or UDP. So this will have the protocol number for that. Hold on. But now here, before the TCP comes, you might have some other IPv6 headers. They have a number too. All right? Go ahead, question.
Yeah, why did they remove fragmentation?
Because they felt that there was too much waste of time of the routers, and therefore the only way to send the packet would be that you first find out what is the MTU and then send that.
So you always get ICMP.
You will get an ICMP. Basically, you send a packet and then you'll get an ICMP, and then all right.
There's no fragment.
So basically, no fragment bit is set by default. All right. Protocol type file, now the next header, time to live replaced by hop limit, so they wanted to be truthful, and they added priority and the flow label. So they added priority. There was no priority before. Before they had actually something similar which was called type of service, 4 bits, now they call it priority. And flow label. So what is a flow label? Basically, by this time, by 1995, we started realizing that many packets are related. And so if the many packets belong to the same application, maybe they should get the same treatment, they should get the same priority, they should get this, whatever, quality of service. So we put a number which is, say, this is the flow number 15, this is the flow number 17. So when the application sends, or the source sends the packet, it puts the flow label, and then the routers treat that whole flow as one, basically with the same quality of service. So the flow label field was put. All right, so, and then flow level now, all fixed size fields, and now there are no variable size fields, like before where you had the options and other things, no optional field, but you have optional headers. So whole set of fields are optional together. 8-bit hop limit. So the hop limit is 255, which was actually before, and people would say, why didn't you increase that? Well, by that time it was understood that really the number of hops doesn't go up as the number of devices goes up. You could have now, instead of 4 billion, you might have 4 trillion or 4 whatever quadrillion devices, but the number of hops will still remain limited to 55. The next header field, for example, 6 means TCP and 17 means UDP. So that is the protocol number for TCP, this is the protocol number for UDP, 17. If that field says 6, that means the next header is TCP, right? But before it says 6, it will say something else for IPv6 headers. So IPv6 headers, let's see them for a minute. We will talk about them in a minute. But one of the problems that they made a mistake on is this whole transition strategy. They did not really think about as to how the world will transition to 6. And the answer was very academic answer. Very academic answer. It said that the routers will implement both IPv4 and IPv6, which sounds good in the university, but doesn't sound good when you go to buy a router and they say, well, you have to pay for twice as much. So dual stack. Dual stack means each IPv6 router will also implement IPv4, and IPv6 is used if the source host, destination host, and all routers on the path are IPv6 aware. So here's the thing though, if you want to use IPv6, everybody has to know IPv6. If you go into your computer, regardless of what computer you have today, you have IPv6 in your computer. Microsoft has implemented it, Apple has implemented it, Linux has implemented it. So there you go. Everybody has implemented it, but routers have not. And if some routers have implemented it maybe in China, but maybe not here. If here some implemented it, maybe one is not implemented. If one has not implemented it, then nobody can go through. Right? So there is no such thing that the whole world will change one day to IPv6. It has to go gradually. That gradually it cannot happen. Right? That's why in 21 years there is no IPv6. So the thing is, it does work in those countries where it is being used. But as soon as you get out of those countries, you need to get back onto IPv4.
I just saw the slide and thought maybe converts it.
Yeah. So you can do the tunneling. So that's another answer. So the next answer is tunneling. Tunneling means that you really don't, you put a packet inside a packet. You take your IPv6 packet, complete packet, including the header, and put it inside an IPv4 packet. And then you send it where IPv4 ends. So this is IPv4 land, this is IPv6 land, this is IPv6 land. If you want to go through IPv4, you dig a tunnel. That means you basically put this packet here, it goes from this router to that router, B to E.
How does B know he's IPv4?
Well, B knows that I speak IPv4 because it speaks IPv4. Even though it is speaking IPv6, it also speaks IPv4 because it is talking to an IPv4 router.
I'm just asking, how does he know he's IPv4?
Yeah, so every router knows the network configuration, and they know exactly where everybody is and what they speak. So this router knows that the maximum I can go, and I want to go to D, by the way. B knows that I want to go to D, and therefore the maximum I can go on B4 is E.
So what happens is you send an IPv6 packet?
Yeah, you start from IPv6 here,
Then
it becomes IPv4.
IPv4.
Yeah.
He knows E's IP address, so it sends it over
To E.
IPv4.
E opens the packet,
Opens the packet, gets IPv6, and
sends it on. Yeah. Tunneling is clear. Another name for tunneling is encapsulation. Yeah, go ahead.
So each router knows the configuration because of that Ethernet broadcast.
Okay, so each router knows at least the same protocol routers. I mean, each IPv4 should know all other IPv4 routers, right? And towards the end of this lecture, this chapter, we describe as to how they exchange all this information and they find out. So routing is, we haven't covered routing yet. We are still talking forwarding, right? So how to make the routing table and how to find out who is where and all that, we will talk about that. All right, but key point here is tunneling. Everybody understands tunneling. What is tunneling? Encapsulation. Packet inside a packet. Understood? Okay. All right. So that is the end of IP. And the key points to review are that IPv4 uses 32-bit addresses, which now into two parts. One is the subnet part and one is the host part. Subnet part is no longer fixed. In the beginning it used to be fixed, 8-bit, 16-bit, 32-bit, 24-bit, and we call them ABC classes. But now we have CEDAR. CEDAR means classless, class independent or something like that, right? Routing. So that means we don't have any more ABC, we can have any number of bits. Private addresses can be reused, and private addresses can be reused and help solve the problem to a great extent. ICMP is the IP control protocol for the error message that we discussed today. We discussed DSCP to automatically assign the addresses, and IPv6 uses 128-bit addresses, but it requires dual stack or tunneling to coexist with IPv4. When IPv6 was discovered or was designed, by that time we were much more intelligent about networking, and so a new class of addresses was discovered or put into IPv6 called link local. The idea of the local addresses was slightly different than private addresses. The local address was that if you have an Ethernet link, then any host on that could talk to each other by using link local addresses. Those addresses cannot get out of the link, but they can talk to each other using that address. Okay, for example, inside your home, your mom calls you something and you call your mom something. So you can call your mom, but you cannot send a packet outside of your home addressed to mom. Right? It has to be addressed to Mrs. So-and-so with full last name. So inside the link, you can use some special addresses that are good only inside the link. Just like private addresses cannot get out of private network, the link local addresses cannot get out of the link. Then they also had site local. Site local means they can stay in one campus. They cannot go to medical campus. Then they had a organization local or something like that, enterprise local, I forget the name. So they will not get out of Worcester if they want to get out. That is like a private address anyway. So they had many local addresses. So the link local addresses concept was then taken back into IPv4, and a set of addresses were reserved for link local use, and that is 169. Now I forget the exact number, but let's just for the time being take that is 169.0.0, so 169/8. I could be wrong on that one. Okay? So that address range is reserved that anybody can use. So if you put an Ethernet thing together and you don't have a DSCP server and you put 4 computers on it, they can assign it themselves. All right? And they can talk to each other without DSCP server. But they cannot talk to anybody outside. You understand? And so that was the purpose of that address. Now there is a problem with that link. Out of that, 512 addresses were taken out. So first 256 addresses are reserved for future use, and the last 256 addresses are reserved for future use. So the range is not exactly this. The range is minus the first 256 and the minus the last 256. To be confusing. But anyway, the way you assign that address to yourself is that you select any random number in that range, and then you say, this is my address. And you send a packet to yourself. If you, actually there is another protocol which is used, ARP or something like that. And if nobody else has that address, then you're all set, you can use it. If somebody else has that address, then you select another random number. So by this method, any network can be started without having a DSCP server. Link local address.